This lecture is a demo on a sample problem for cells and batteries. Example number one, there are 30 cells arranged in 5 in series and 6 rows in parallel. The internal EMF of the cells is 1.4 volts each, and internal resistance of each cell is 0.08 ohm. Required here is the total EMF of the combination, which is the total internal resistance. This is the R total, and the current to the load with resistance of 4 ohm. This is the R sub L, and required here is the current going to the load. Let's name this as I sub L. And the terminal voltage, which is V sub T. The 60 cells, five cells in series. So each cell is 1.4 volts and internal resistance is 0.08. We need to transform this circuit into an equivalent single cell, and so that we can apply the formula for single cell. So to come up with a single cell, we have to simplify this one step at a time. First is we have to combine all the cells in series into one cell. Let's name this as E sub 1. So all of this to become E sub 2, E sub 1 and R sub 1. And here is cells shall be E sub 3 and R sub 3, E sub 4 and R sub 4. This would become E sub 5 and R sub 5. And this would become E sub 6, R sub 6. So all cells shall be replaced with a single cell, all cells in series. And since these cells are identical, we can each 1.4, we can simply multiply the 1.4 with 5 to get the total equivalent internal EMF, E sub 1. In the R sub 1, we can multiply this 0.08 also with 5, because there are 5 cells in series. And the circuit would become as simple as this circuit with 6 identical cells in parallel. So this is 5 cells in series times 1.4 is 7 ohms. And since they are identical, having the same internal EMF, we can say that the total internal EMF equivalent total internal EMF is equals to 7 volts. Now for the 5 cells in series, you have to multiply the internal resistance with 5 to get the internal resistance of R sub 1, R sub 2, 3, 4, and 5 and 6 equals to 0.4. So they are all again, these internal EMFs are equal because the cells are identical. So we have now 6 cells in parallel, identical cells. Now, since identical, the total internal EMF is already known, which is 7 volts. We are now to compute the total internal resistance of the cells in parallel. The total internal resistance of the cells in parallel, 6 cells in parallel, so we can simply divide 0.4 with 6, and that is the total internal resistance. Then we come up with the total internal EMF 7 volts, total internal resistance which is 0.067 ohms, and the R sub L is 4 ohm. We can now calculate either I total and B total. So now to calculate for the current that goes to the load using this formula, since resistances are available and the total is available. So we have the current to the load, or the current delivered by the battery, equal to 1.72 amperes. The total current delivered by the 60 cells. And then the terminal voltage, it can be determined either using the IRL or the E total minus the drop in the total internal resistance. So getting the voltage across the terminals, that is by multiplying 1.72 with the load resistance of 4 ohms. This may be also determined using the E, which is terminal 7 volts, minus the current, which is 1.72 amperes, times the total internal resistance of 0.067, and this will give you the same answer, 6.88 volts. For the second example, these are two batteries in parallel with having internal EMF not equal, or these are batteries that are not identical. So we have the E1 equal to 50 volts and E2 equal to 53 volts. I will approach this purely using the equation derived from the above discussion, from the previous discussion regarding batteries. But an I sub O, the circulating current, would be calculated from the formula derived. It is equals to E sub 1 minus E sub 2 over R sub over resistance R1 and internal resistance R2. So I will simply follow the formula without regards to the magnitude of the internal EMF, and that ISABO would be simply 50 volts minus 53 divided by the sum of the internal resistance, and this would give us negative 30 ampere. The negative 30 ampere simply means that the direction of the ISABO would not be coming from E sub 1, instead it should be coming from E sub 2. However, the assumption that E sub 1 would supply the ISABO could still be used as long as the negative sign of the ISABO would be considered every time the ISABO is used. So do not neglect the negative sign of the 30 amperes, which means that it is not coming from E1 but instead it is coming from E2. However, this assumption, the direction of the assumed ISABO simply means that it is incorrect. Then to get the total internal EMF of the combination, we can use the E sub 1 minus the I sub O R sub O. This is strictly following the derived equation. So the E sub 1 minus the negative 30, the minus and negative would result to a positive, meaning there is an increase in voltage at the circuit of E sub 1. It is because E sub 1 is has a sufficient voltage compared with the circuit of E sub 2. So there is a shortage of voltage in the circuit of E sub 1. The voltage E total may also be determined using the circuit of E sub 2, which is E sub 2 plus the I sub O times I sub 2. And this would be equal to 50. This is what? How much? 53. So this is 53 plus the negative of 30 times 0.04, and this would result to the same value, 51.8 volts. There is a decrease of voltage in the circuit of the E sub 2. E sub 2 gives off the 30 ampere, and so therefore the voltage at its terminal would decrease to 51.8. In this case, the circuit of E1, E2 are now rationalized to a certain voltage, which is 51.8 volts. Or you may apply the formula without using the circulating current. Then computing for the total resistance, internal total resistance, two resistors in parallel, we can apply the product over some formula. And this equals to 0.024 ohm. So we can be determining the terminal voltage. We have computed the value of the total internal EMF and the total internal resistance. The current that is going to the load was known. It's a 48 ampere. Then we can now determine the terminal voltage. That is 50.65 volts, 648 volts. Now, to calculate for the current, we can use this is the current division. To calculate for the current division for the current supplied by each battery, we can again apply this formula individual for the individual circuit of E1. So that is E1 minus the common terminal voltage V sub T divided by the internal resistance of the battery. This gives us negative 10.8 volts, and the negative means that the battery is not delivering any current. The battery is on charge. It is charging. The battery is not supplying any current. It is acting as a load, and it draws current from the battery E2. The I sub 2 is equals to the E2 minus Vt over the internal resistance, and this was a current of 58.8 ampere. So all the current in the circuit was supplied by the battery E2, and we can sum up. If we sum up the current in the circuit, this E2 is actually equals to the 48 ampere supplied to the load, and plus the current of 10.8 amperes supplied to the battery 1. What does this problem implies? It implies that it is not advisable to connect two batteries of different internal EMF. It is because that the battery having low internal EMF would become a liability in the circuit. That is why it is advised that when you connect batteries in parallel, it is advised that batteries should be identical. And if you are going to connect batteries, though identical, but one is old and one is new battery, it is not advised, simply because the internal EMF of an old battery is much lower than the internal EMF of a new battery. The old battery would simply act as a load.